So in the previous lecture, we were talking about the network device, which is used in the network layer side. So that is your router, and how those routers are used to connect the end devices from the local area network to your public area network, and what are the basic properties of your network devices that we have observed. So some other devices which are used, let me just change the pin. Okay. So that fine. Sorry. Just give me a second. So other network devices other than your router, we can see the hubs, bridges, and your LAN switches. So which are used at a different layer in the TCP/IP suite, the hubs, bridges, and the LAN switches. So we'll see this one by one. So as the Ethernet hubs act as a multi-port repeater, simply we call them, because they don't do any multiplexing, or they will just take the packets from input line and forward the packets through their output line or output interfaces. So these repeaters that just receive the incoming electrical signals or the data on a port, and it then immediately forwards a regenerated signal out for all other ports. So if it is having the multiple ports here, so whatever the input packet is there, that input packet simply forwarded to all the output ports. So these hubs, we can say one type of giving, regenerating the signal if it is, as the packet travels through the physical media, they try to lose their energy. So these hubs, they try to reboost the electrical signal so that it can go to the destination side without any errors during the transmission. So they do not look at the source and destination MAC addresses. These hubs, they just think about the signal process itself. If the hubs connect to the network into a star topology, with the hub as the central connection to any of the star topologies, like if any other device is connected, suppose computer 1, computer 2, computer 3, and suppose your computer 4 is there. If they are connected in this fashion, we call it as star topology. So if it receives from packet from any of the computers, it will simply broadcast it to all other computers through those output ports, which are there from this hub side. So then comes to the next part is the bridge. So this bridge have the two interfaces and are connected between your hub to divide the entire network into the multiple collision domains. So each collision domain have only the one sender at a time, and all other ports are going through the receiver side. So whereas your LAN switches, these are having their own operating systems, so they try to find the instead of doing the broadcast, they try to do the one-to-one connection or one-to-one packet transfer or one-to-many packet transfer. So these LAN switches are essentially the multi-port bridges, which are similar to your bridges, but they connect devices into the star topology like your bridges and hubs, but switches segments a LAN into your separate collision domain, one for each switch port. It is having multiple ports. Then it can find out if this port is, suppose, busy with transferring other packets. So then you try to avoid that particular port to forward that packet and go through the other ports which are collision free. So a switch that makes the forwarding decision that is based on your Ethernet MAC address. So in this, figure these are the basic communication devices which are used. So here at the hub you can see that it go through the broadcasting one, but whereas your bridge is also try to find the collision free domain, so that the packets which are transferring within the network, they cannot collide to each other and get any damages. So you can see one of the switching operations here. The switching operation means the switches, they use the MAC addresses that we know it is a physical address. So the switches use the MAC address, means it clearly indicates that the switch belongs to which layer of your TCP/IP suite? It belongs to the physical layer. It belongs to a physical layer. Whereas if a device is using the IP addresses, means that belongs to your network layer. So in this, it is very clear that this the MAC address which is assigned to any of the device, that is used by the switches to direct the network communication through the switch. So to appropriate, based on the MAC address which is available at your switch, it will have the address resolution protocol also. So your ARP table will be there. In that ARP table, it finds the IP address as well as their MAC address mapping. So if any device which is sending a particular packet to any of the hosts, to computer, then it just examines the packet header. From that header, it finds the MAC address. Based on MAC address, it finds which line is connecting to the destination, which port is connecting to the destination. If it is having multiple ports, the appropriate port based on this MAC address will be selected and the packet will be forwarded through that line, so that it will not go through other ports, and that will avoid the collision in the network. So a switch is made up of the integrated circuits and the accompanying software that controls the data path through the switch. So for a switch to know which port to use to transmit a frame, it must first learn which device exists on each port, that is based on their MAC addresses. So it builds this ARP. So as the switch learns the relationship of port to your device, it builds a table we call the MAC address table or address resolution table, or we call the content addressing memory table, or the CAM is a special type of memory which is used in this, the high performance, the high speed searching application part. So the LAN switches, they determined how to handle the incoming data frame by maintaining these MAC addresses. So a switch that builds the MAC address table by just recording the MAC address of each device that is connected to each of its ports, we call that your MAC address table, or your ARP table will be there. So then the switch use this information in the MAC address table to send the frames to destined for a specific device which is out of the port to which the device is connected. So there are two-step process is performed on every Ethernet frame that enters a switch basically. So one is it learn that is the examine the source MAC address of your frame. That is first operation it performs. So learning, that means it examines the source MAC address of your frame. So in this diagram you can see the the table which is maintained by your switch, that is the MAC address table. For every port, if any device wants to communicate with any other device, they are connected to each individual ports here. So in this individual port, when this the computer A try to send a message to any other device, then upon receiving the packet, we call that Ethernet frame. Upon receiving that, it is trying to build a MAC address table. In the MAC address table, the entries are, one is your port entry, another one is the MAC address. That means on port 1, the MAC address of that computer is associated. Right? So that every frame that enters the switch is checked with for the new MAC address information by examining the frame's source MAC addresses and the port number where the frame enters into the switch, this port number. So if the source MAC address is not in this MAC address table, then it is added to this MAC address table along with its incoming port. So if the source MAC address is already exists in the table, then switch updates the refresh timer for that entry, means at what time again the same entry is taken place. So by default, most of these switches, they keep an entry in the table for 5 minutes basically. The reason behind this, why this MAC address is kept for only 5 minutes, do you find any importance for this maintaining only 5 minutes in the table? In terms of network attacker, if you think in that direction, then you can find out why only 5 minutes will be maintained, or maybe if it is manually set to suppose more than 5 minutes, that is also possible. But as short duration is maintained, it is best to avoid the vulnerability. So you might have observed that the nodes which are there within the network, they may try to spoof the MAC address and they try to change the direction of your packet transmission, which we observed in previous classes. So to avoid that kind of attack, or to avoid the vulnerability, you try to maintain this MAC address frequently, MAC address table, so that if any vulnerable entry is there from any attacker, they claim that from port 1 the MAC address, instead of your 0A, if 0D is suppose the attacker in this case, they may claim that for port number 1 the MAC address is D, so that all the packets which are destined to your computer A will be forwarded to your computer B, because based on this MAC address. So to avoid that, it is required to update this the switch, the MAC address table very frequently. Okay. So this is the first operation of your switching, that they examine the source, the MAC addresses, and if the address is there, they will just try to update it in every 5 minutes. If the addresses are not there which are associated with this port, then the new entry will be take place in this MAC address. Like for port number 2, the MAC address computer 2 is, the computer B is assigned. For port number 3, from this diagram, the MAC address 0C is assigned. For port number 4, the 0D is assigned. So any packet that comes, your switch will go through the destination. So once this MAC address is built, MAC address table is built, then upon if any packet comes to these ports, your switch will go through the destination MAC address and check whether the destination MAC address is there or not in the table. If it is suppose there, then for that particular MAC address, which port is assigned. So through that port, it will simply forward. So it goes to one-to-one communication. So that is the second operation is forwarding. First one is learning the MAC address. Second one is forwarding. So that examine the destination MAC address. The second step. So if the destination MAC address is a unicast address, so it will have only one MAC address, right? So the switch will look for a matching between the destination MAC address of the frame and an entry in its MAC address table. If the destination MAC address is in this table, suppose, then it will forward that frame out to that specified port. So whether it is to the port number 1, 2, 3 or 4, it will forward to it. If the destination is not there in this MAC address table, then the switch will forward that frame out to all ports except the incoming port. It is just like you are broadcasting. So if address is there, then it will do the unicasting. If the address is not matching in this MAC address table, then it will do the broadcasting. So in that broadcasting, only thing is, except the incoming line, it will forward that packet to all other ports. Okay. So that is the two-step operation of your switching devices. Okay. So in this let me just play a video for you so that you can get an idea more. Just listen carefully.
PCA is going to send an Ethernet frame to PCB, and PCB is going to send an Ethernet frame to PCA. We're going to examine how switches S1 and S2 build their MAC address tables, and also how they forward frames based on the information in those MAC address tables. PCA has an Ethernet frame to send to PCB. The source MAC address of the frame is 000A, and the destination MAC address is 000B. The Ethernet frame is sent to switch S1. S1 receives the Ethernet frame, examines the source MAC address, and notices that this MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number. Next, switch S1 examines the destination MAC address and notices that this MAC address is not in its table, so it floods it out all ports. PCB receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices that that is a match and receives the rest of the frame. The Ethernet frame continues to be forwarded to switch S2. Switch S2 examines the source MAC address of the frame and notices it is not in its MAC address table, so it adds the MAC address and the incoming port to its MAC address table. Next, switch S2 examines the destination MAC address, notices that is not in its MAC address table, so it floods it out all ports. PCC receives the Ethernet frame, and its MAC address does not match the destination MAC address of the Ethernet frame, so it does not accept the rest of the frame. The router receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notes that it's not matched, so it does not receive the rest of the frame. Now let's have PCB sending a frame back to PCA. The source MAC address of the frame is 000B, and the destination MAC address is 000A. PCB sends it to switch S1. S1 notices that the source MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number. Next, switch S1 examines the destination MAC address and notices that MAC address is in its MAC address table, so it sends it out just port 1. PCA receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices it is a match, so it receives the rest of the frame.
So, that's the way how it builds the table also. So in the learning process, if any MAC addresses are not there, so initially when the network installation happens, so there is no entry in the switch because every device is new. So whenever they try to communicate with other device, it directly goes through the switch. Okay. So when it directly goes through the switch will learn which packet is forwarding inside the network. So based on that Ethernet frame, your switch can build the MAC address table. So like that, as the communication starts and goes on, your MAC address table becomes full. Because if as the time goes on, communication goes on, every device in the network, if they try to communicate each other, so every device MAC address and their associated port number will be taken as an entry in the MAC address table. So once that table is built up, then we say that the timer will be set for that MAC address table by the switch. By default, 5 minutes, or manually from the network administrator, they may set it to 10 minutes. Or they may reduce the time also. Right? So in that, you can also observe that we found two different switches, switch 1 and switch 2. So the Ethernet frame not only circulated or forwarded within the switch 1 connected devices, also forwarded it to switch 2 device. So when switch 2 is trying to forward the packets to all other nodes, okay, it also placing its entry, the PC1 entry in switch 2 table. So any device in the network, just go back, if suppose the MAC-C, if suppose the PC-C wants to communicate with PC-A or PC-B, in that case, in the first case, suppose with PC-A, when that packet Ethernet frame goes to your port number 2, your switch 2 will check in this MAC address table whether port 2 is associated with any of the MAC address or not. If it is not there, then this entry will be take place here and forward that packet directly to your switch 1 port, because it is mentioning that the address is from this port number. From this port number, it is assigned to your computer 1, which is connected to your switch 1. So upon forwarding this from your switch 2 to your switch 1, switch 1 go and check in its address table that what is the MAC address. MAC address is A, and which is connected to the port 1, so it will unicast it. So yeah.
So on switch 1, it's going to say port 4 as 000C, because that's where they're connected.
Is it in switch 1 you are talking about? Port 4 is connecting to switch 2.
Right, but so if it was going to, if switch 1 was going to store the MAC address for the computer on switch 2, it would do it on port 4.
Yeah.
Because that's where they're connected.
Yeah. So here entry port 4 is having the MAC address of your switch 2. In this. And in this, your port 1 is having the MAC address of your computer 1, which is connected to your switch 1. So what happens here, if switch 2 is sending any packet, then in this table, the MAC address of your switch 1 table will be having the entry 4 with switch 2. So that is the, that we have seen in end-to-end packet forwarding. Switch 2 is the end device of your switch one in this case. So upon it is receiving that packet, I am forwarding that the MAC address of your switch 1 and switch 2, they are changing the information which called the routing information exchange. Yeah, so that is the concern between the switch communication device, and why these switch devices are used, that we can check it out, that the virtual LANs will be formed with this switch 1 device we call the VLANs. So within a switching network, the VLAN that provides the segmentation and organizational flexibilities for identifying and speed up the network bandwidth or speed up the network throughput. So this VLAN provides a way to group the devices within the LAN, like VLAN 2, VLAN 3, VLAN 4. So they're grouping the devices to easily identify and easily forwarding the packets. So a group of devices within a VLAN that communicate as if they were connected to the same network segment. So these VLANs are based on the logical connection instead of the physical connections. So these logical connections, they try to separate these group of devices. As we discussed, if you have the hundreds of computers, you can divide them into the groups, like in this case, in floor 1, floor 2, floor 3, you divide those, computers based on the VLAN configurations or virtual LAN configurations, we say. So like the IT group in floor 1, and in floor 2, suppose your HR group, and in floor 3, suppose the sales group, like that. So this VLANs allows an administrator to segment the network based on the factors such as their functions, projects, teams, or your applications like your IT, HR, and the sales type. So these devices within these virtual LANs like IT group or your HR group or sales group, they act as if they are in their own independent network. So even if they share a common infrastructure which are used to connect these the computers, but they feel that they are in a separate group. So even if they share this common infrastructure with the other virtual LANs like virtual LAN 3, 4, this virtual LAN 2 group devices thinks that they are having their separate network. So this is any switch port that can belong to this virtual the LANs. It may be switch 1 or switch 2 or your switch 3, the ports which belongs to this virtual LAN. They use the unicast or broadcast or multicast packets are forwarded and flooded only to end devices within this the virtual group or virtual LAN. So with that, what happens? That packet is not forwarded to any other group. So the network bandwidth will be used by only the devices which are connected to this network. I mean the VLAN. So that reduces the network traffic. When network traffic is reduced, it automatically controls the congestion. Congestion control can be easily possible. So the packets which are destined for these devices that do not belong to any other, the virtual LANs must be forwarded through a device that supports the routing. So in this virtual LAN that creates a logical broadcast domain that can span the multiple physical LAN segments. So this VLAN that improves the network performance, as said, by separating the large broadcast domains into the smaller ones, And if a device in one virtual LAN sends a broadcast Ethernet frame, suppose, then all devices in the virtual LAN that receives that frame, but devices in other virtual LANs, they don't receive. So these VLANs also prevent the users on different the VLANs from snooping on each other's traffic. So in this example, if you see that even though the HR and sales are connected to the same switch in the figure, this group of computers which are connected to the same switch in this, so the switch will not forward the traffic between your VLAN, between these VLANs. So that means the traffic which belongs to the group of computers belongs to your IT will not be forwarded to HR groups, though they are connected to same switch. Okay, so this is the advantage of your virtual the LANs for the, to improve the performance of your computer. I mean the network. So another the network communication device we call the STP, that we call the spanning tree protocol, is basically used in the switches to maintain the one loop free path in the layer 2 network, in the physical layer 2 network. So the network redundancy is a key to maintain the network reliability. So the multiple physical links between devices provide redundant paths. So the network can then continue to operate when a single link or port has failed. So these redundant links can also share the traffic load and increase the capacity actually. So this multiple path need to be managed so that the layer 2 loops are not created and that will give the loop free in the layer 2 network at any time. So the best path are chosen and an alternative path is immediately available should a primary path fail. So the spanning tree protocol is used to maintain one loop free path, as said, in the layer 2 network at any time. So this redundancy increase the availability of your network topology by protecting the network from a single point of failure in the network. So that happens because purposefully, if any of the attackers try to find that particular single port, and if that port wantedly become down, or wantedly trying to make that port as down, then if every packet which is going through that will not be reach to the destination side. So this as said, the redundancy increase the availability of your network topology by just protecting the network frame as a single point of failure. So such as a failed network cable or switch that is possibly happen. So when the physical redundancy is introduced into a design of the loops and the duplicate the frame, it occurs. So these loops and duplicate frames have the severe consequences for a switch network. So this STP, the spanning tree protocol that was developed to address that particular issues in this. So this STP protocol that ensures that there should not be any logical path between all destinations. So there is only one logical path will exist between all destinations and the network by just blocking this redundant port. So this STP ensures that there is only one logical path and on the network. So a port is considered as blocked, as we said, and the blocking the redundant path is critical to prevent the loops on this network. So the physical paths still exist to provide this redundancy. So, but these paths, are disabled to prevent the loops from the occurring. So, if the path is ever needed to compensate for a network cable or switch failure, the spanning tree protocol recalculates the path and unlocks the necessary ports to allow the redundant path to become active. So that is the advantage of your STP, the protocol for maintaining the network stable and increase the performance of your network. So how it is means, if for whatever the n number of packets are sent from source to your destination, if all those n number of packets are frames are received by your destination, we say that the performance of your network is 100%. But if the out of n number of packets, if n by 2 number of packets only received by your network, means the performance is basically 50%. It gives the 50% of your performance because some of the packets are lost. So we'll see in the multi-layer switches is another type of switches which are used to increase the performance of your network. So these multi-layer switches we also known as your layer 3 switches. So that is not only perform the layer 2 switching, these multi-layer switches, but also forward the frames based on your layer 3 and 4 information. So what is layer 3 and layer 4 information? In the layer 3, you will have the information of your IP address, the IP version 4 addresses, and at the layer 4, you are having the port numbers, the TCP port numbers. You are using the whether it is port number 20, 21, 22, means whether they are belongs to your FTP or your TFTP. So based on that. So these most of the Cisco the Catalyst multi-layer switches, they support the layer 3 interfaces. So when layer 3 interfaces comes, they routed based on their port. So a pure layer 3 interface, which is similar to your physical interface and Cisco, the operating system based routers. And another one is your switch virtual interface. One is root port, another one is switch virtual interface. So this interface is for the inter-virtual LAN routing. That is, as we said, all the devices will be divided into virtual LAN 1, your virtual LAN 2 as grouped, V2, and suppose V3. So all the computers, they are grouped in this, which are connected with the same switch. So they use this virtual LAN interfaces for this inter-virtual LAN routing when these devices are trying to communicate with this device or trying to communicate with these devices. So in the first one, this routed port, the routed port is a physical port it is, and that act similar to your interface on your routers actually. So these are these acts as the routers. So what is the job of your router? We have observed that router having the routing table. In that routing table, the entries are what is the source IP address, what is the destination IP address, and what is the interface which is associated with this, that we call the what is the next hop. So based on that, the routing table will be formed. So it may follow any static routing protocol or your dynamic routing protocol. So in our previous lecture, we have seen the open shortest path routing protocol that is used to find out what is the source IP address enter in the routing table, destination IP address, next hop, as well as the length of your path from source to the destination. So these routed port are your multi-layer switches. They act as your routers basically. So unlike the access port as shown in this these are the multi-layer switches, and these are the normal switches. So these multi-layer switches, they act like the routers only. So they maintain the routing table. So a routed port that behaves like a regular router interface, and also because layer 2 functionality has been removed, your layer 3 protocols such as your STP, your spanning tree protocol, that do not function on a routed interface. So some protocols such as your LACP, we call them as your for finding the logical address for source to your destination one. So this LACP protocol or your Ethernet channel, they do the functions at layer 3. So this Cisco routers, the routed ports on a Cisco operating system switches that do not support the sub interfaces. So in the next type of your multi-layer switching is your the switch virtual interfaces. So in this switch virtual interfaces, this is a virtual interface that is configured within a multi-layer switch, which acts like your router itself. So this is unlike the basic layer 2 that is based on your Ethernet frame. This layer 2 switch discussed that you just go through the source MAC address and your destination MAC addresses. But a multi-layer switch can have the multiple the switch virtual interfaces. So this SVI can be created for any virtual LANs that exist on the switch. So any number of virtual LANs will be created based using the multi-layer switch. So this the SVI is considered to be the virtual because there is no physical port dedicated to a specific interface here. So it can perform the same functions like your virtual LANs, which are performed by your the normal switches. So it can perform the same virtual LAN as your router interface would, and can be configured in much the same way as your router interface, which find out what is the source IP address and the destination IP addresses for your inbound and outbound of your access control list, to check it out whether the packets are the valid packets or coming from any the attacker side. So this SVIs for the virtual LANs, that they provides the layer 3 processing for packets to or from all these switches which from all these switch ports which are associated with the virtual LANs, virtual LAN 10 suppose and virtual LAN 20s. So it acts like you are the most like you are having the IP addresses, which your IP addresses comes in the layer 3. So that belongs, either it will have the IP version 4 address or your IP version 6 addresses. So in this switch virtual the interface you can see this, how it is further reducing the what you call the load of your the network, so that it is going to categorically it is forwarding the packets to only a group of devices in the network, so that the network resources will be used in a less the uses, so that it will increase the performances. The next one is the wireless LAN operations for the wireless communication. Let us first see a video, and then we'll enter into this wireless LAN communication. Just check it out. Let me just play for you.
One that's jumping to wireless LAN operations. This is wireless LAN. One.
So here you can
Hello,
see.
everyone. That's
Okay. In the wireless LAN, it is based on some of the infrastructure, because you can have some ad hoc mode, means when there is a demand, then and there only the infrastructure will be installed and the communication process will be take place. So in that case, most important part is who is going to forwarding to provide the services to the mobile devices or movable devices in the network. So we find the BSS, that is basic service set, which is used to connect any of the mobile devices. These BSS service providers, they connected with its extended service set we call ESS, and for the frame structure, which is little bit different from the wired networks. In wired networks, we use the 803.1 frame structure, but here the wireless use the frame structure of your 802.11 frame structure for wireless LAN. So here, like your address resolution from your converting, like your network address translation, the private IP address to your public IP address, when it is semi-connected with the infrastructure-based network and some portion is suppose infrastructure-less network, then the IP packets which are in the infrastructure-based network follows the 803 format, whereas this frame structure is 802.11. So there is a frame encapsulation and decapsulation will be take place at the basic service set. So you just see this, and then we'll discuss more about this one.
Hello, everyone. Let's jump into wireless LAN operations. This is wireless local area network operation. And to get started, we need to talk about two different types of modes. We're going to hit infrastructure mode, and then we're going to hit ad hoc mode. First, with the infrastructure mode, we're focusing.
Yeah. So here you can see in this side, you're having the router. Router is connected to the switches, and those switches are used to connect some end devices. And one switch is connected to another switch, that is your wireless switch. From the wireless end devices are connected here, right? So this mobile phone or your tabs or your laptops, they are wireless. So here, this portion we called it as your infrastructure-based network, okay? Whereas this portion we call it as infrastructure-less network. So in the infrastructure-based network means before starting the communication, infrastructure is established first. They're connected with wire, means the cables. Whereas this side, there is no infrastructure. Anytime this mobile can come in the coverage area of this wireless switch, they can connect and use the communication service. And if they are going outside the range of this wireless range, then they will become disconnected. So anytime the device can come inside the network and go outside the network, so there is no standard infrastructure there. So we call that as infrastructure-less service here.
Here on a wireless network that's connected to wireless devices. But that wireless network connected to those wireless network devices is hooked to a wired distribution system. What that means is our wireless router is connected with a wired Ethernet cable down into our infrastructure. That infrastructure of these other two switches here will then carry that traffic on to the router and to the local PCs. You're literally connecting your wireless router with a wireless device, and that wireless router is then having a wired connection to your distribution system. Let's switch over to ad hoc mode, much more basic. And with ad hoc mode, we're talking peer-to-peer. We've got two devices connecting wirelessly without any network infrastructure, without any wired distribution system. A good example of this would be having two phones and literally having two phones directly connected to each other, maybe sharing a file using technologies with Bluetooth or AirDrop, 802.11 comes into play there. But that would be ad hoc. You do not have an infrastructure device. It is directly device to device, known as peer-to-peer. Lastly, you can toss this in as like a extra mode, but this would be tethering. And with tethering, this is where you have a cell phone or a tablet with cellular data access connecting to cellular internet. But that cellular device is also running as an access point. We would call that as a hotspot. So while the cellular device itself is having a connection to the internet, it is also creating a wireless signal for wireless PCs, wireless tablets, and other devices to connect to the phone or tablet that's running cellular as a wireless router. From there, our devices that do not normally have cellular data access, they can connect through that cellular data device, and that's called tethering. It really is similar to ad hoc, where we're going to be using a peer-to-peer from our, let's say, laptop or from a non-cellular data device with this cellular device. And then that cellular device itself will connect out to the cellular data network. So it's time to switch it up a little bit. We're going to need a couple new terms here like BSS and ESS. So let's dive right in. BSS is Basic Service Set. A basic service set is where we talk about providing wireless access to small deployments. A basic service set will include a BSA, known as a basic service area. These yellow bubbles, for example, are basic service areas. That is the extent of the wireless signal that is possible to connect to with that access point that we see here. The BSS ID is the basic service set identifier, and that's going to be the layer 2 MAC address of your access point you're connecting to. So here's one access point, and that's the BSS ID, which is what you'd be connecting to inside of your basic service area, the laptop in that signal range. Here's another signal range, or BSA, basic service area. There's a separate access point, and that access point has its BSS ID. That's the formal way that we recognize the access point, which again is the layer 2 MAC address of that access point. Now the thing is, this doesn't scale. And if you're talking about larger networks and scalability, we're going to flip over here to the ESS. With the ESS, known as the Extended Service Set, we're going to have one huge, large area of coverage. And that large area of coverage that we're going to be seeing here is based off of having multiple BSAs, or basic service areas, deployed. But they're deployed in such a manner that they're all connected to one single wired distribution system. So we have multiple access points, each access point having its BSS ID, with devices connecting to those access points, and those access points being connected to that wired distribution system. And the cool thing about this is it promotes roaming, which means this user over here on the far left side in this BSA can take their laptop and walk over into another office and hook to another access point on the same wired distribution system. And with roaming, it would be seamless for that user. They don't have to disconnect from one wireless SSID and connect to another one. It will be seamless. So let's continue on through our conversation as we connect to these access points. What do we have to worry about? Well, you don't have to worry about this, but at least it's something to learn. And that's called 802.11 frame structure. We're not going to rip it apart, but we can talk about it. This 802.11 frame is similar to what we've seen in 802.3 Ethernet and NET's frame, but we've got more fields. We've got here frame control, duration, multiple addresses, sequence control, and then even an address for it. What it comes down to is we have to concern ourselves with how our devices are going to be connecting to an access point or a wireless router, and that might be the middleman in our conversation to eventually have this traffic reach a web server on the internet, like Cisco.com. So we have this middle device to work through. Well, how do we do that? Well, with these different fields inside of this frame structure, we can use things like address 1, where address 1, for example, would be the MAC address of the receiving wireless access point. Address 2, for example, would be the MAC address of the transmitting wireless device, like your cell phone or a tablet or the laptop you're on. Address 3 might even be the gateway device. This might be the router that's going to be the default gateway of the network. Think of all the different devices that your wireless client will have to get through to eventually leave its local area network when you're referring to having wireless and this wireless technology in the middle. We have control sequencing and fragmented frames coming up in sequence control. Address 4 could be used in our ad hoc modes. In frame control, we have to worry about power management and subfields for different protocol versions and frame types. And finally, don't forget this big, huge area of payload. Payload is the data of your transmission. And then FCS, for a frame check sequence, that's your error control. So all this comes into play to help us connect out with our wireless end devices. And speaking of wireless end devices, feels like there's a constant battle because everything is going wireless and it all wants to fight for bandwidth. Well, how do we gain access with many wireless devices to a single wireless access point? Well, there's a technology that's going to help us out, and that's called CSMA-CA. CSMA-CA is Carrier Sense Multiple Access Collision Avoidance. And really what this means is we're not going to allow traffic just be colliding into each other, flying through the air as all these different laptops and smart devices are trying to interconnect across an access point. We have a better way to go about it. With Carrier Sense Multiple Access Collision Avoidance, you slow that down and speak it a couple times. That's really what's about to happen. What do I mean by that? Carrier Sense. We're going to listen to the wireless media. Multiple access. We have many devices that want to use the same media at the same time. Collision avoidance. We're going to make sure they don't all ram signals into each other and then corrupt that signal. So what does it mean in the most basic sense? We're going to have our wireless devices listen to the wireless channel and see if it's idle. See if there's no other traffic currently on that wireless channel. That channel is just called the carrier. We're then going to have the RTS. Your end device, your computer, your PC, the laptop, the tablet, is going to send a RTS. And this is a ready-to-send message. That message will be heard by the access point. And the access point can then provide dedicated access to the network. Well, how does the end device know that the access point is ready? The access point will respond to that RTS, the ready-to-send. It'll respond to it with a clear-to-send, a CTS. It says, the dedicated access is ready for you. Go ahead and send. When the wireless end device hears that, it's going to then send and transmit its data. And by the way, all of our wireless transmissions are going to be acknowledged. And if the wireless end device does not receive an acknowledgement back, then it knows there was a collision. It's going to restart that entire process back from listen. In order for us to first communicate with a wireless network, though, we do have to associate with the wireless access point or wireless router. And all associating means is we need to agree on specific parameters being used by these wireless network devices, as in the wireless access points or wireless routers. So how it works is this. Our device is going to try to communicate on a specific SSID, which is your wireless network name, with a password, and then using a specific network mode. For example, the wireless router or wireless access point might be supporting 802.11a, b, g, n, ac, or ad wireless LAN standards. Your device has to agree to use that standard in order to communicate with said wireless router or wireless access point. Now, some wireless routers and access points can support multiple standards at the same time, and that's known as mixed mode. Besides agreeing on the mode to use, your wireless end device also has to agree on the security. And that could be your WEP, WPA2, WPA, along with the encryption standards of TKIP or AES. When you have agreed on using the correct one with the access point, hey, those are agreeing on parameters. And lastly, we have radio frequencies, which are our wireless channel settings. We need to make sure that we have an appropriate channel set with our wireless router, wireless access point, and our wireless clients will connect on that. When all that has been done, then we can successfully say we've associated with a wireless access point. Now, when we talk about associating with wireless access point, it's usually very easy. You go on your wireless client, you'll click refresh to see the wireless networks nearby, and you'll hear about them. You'll hear about the name of them, which will be the SSID. You'll hear about the standard supported, which will be the 802.11 standard used. And also you hear about the security settings in place that access point or wireless router requires. All of that's being provided via a beacon. The default, standard, easy access wireless mode is known as passive. In passive mode, wireless routers and access points are on time intervals and sending out beacons, and the beacons includes all that information. But there's another mode, and it's called active. And in active mode, our wireless client, well, there's an issue here. The wireless client isn't going to hear a beacon being sent by default by an access point. And what needs to happen in order for a wireless client to successfully access the wireless network is we can manually configure the SSID and the supported standards on the wireless client. And when the wireless client has the wireless network name on it, which is the SSID, and it has the correct standards to use configured on it, only then are we able to gain access to that wireless router or wireless access point. So the easy way, that's passive, that's the default. The more difficult way of connecting to the network would be using the active mode. So take your time, read through the material for wireless LAN operation, and enjoy picking up some awesome wireless skills.
So this is the overall the picture of your wireless devices. So they use the 802.11 standard of your frame, and the channel which they are using is the wireless channel. So when they are using this wireless channel in the network, when we use the wireless channel, then the wireless channel, it should follow the certain standards that the channel should not be having any collisions. So that we call the collision-free channel. So carrier sends multiple access with collision avoidance. The mechanism is used. That means if any device trying to send a data in the network, first they sense the commonly used channel. If that channel is already busy with some of the data, then it will stop, wait for another random period of time to check whether the communication channel is free or not. So that the first step is it listen to the channel to see if it is ideal or not, and after that it try to send a ready to send message, that RTS we call, to the access point to request a dedicated access to the network, and it receives the clear to send the information from the access point that okay, now channel is idle, you can start transmitting the data. Then it's so that way of in the TCP we use the three-way handshaking first to establish a connection. So here the mobile device that sends the RTC, first it listens the communication channel, then sends the RTC and get the CTC, that is clear to send from your access point. And then if the wireless client does not receive this RTC message, that means it waits another random period of time and then start communicating. So there are two ways of the in this wireless communication from your wireless client to your access point association. One is active mode, another one is your passive mode. So in this active mode, what happens? The manually send the wireless client in the active mode that the SSID and supported standards for authentication purpose, and it will get the response from your access point if your access point is free, right? So that is the difference between active mode and your passive mode of your devices. So with this, we'll try to end the network communication devices. In the next class, we'll try to start the network communication, the network security infrastructure, how using this network devices, how the infrastructure will be installed, and based on that infrastructure, how your network will be made secure, not only network, even your end devices also. So that we'll try to discuss in the next class. So with this, I would like to stop the session. So if you have